today. That's good because I forgot to record. So whether we like it or not, we live in the age of polymers. That is plastics everywhere. So these are plastic containers you'll find around the house. Regular old household containers for soap or laundry detergent or cleaning solutions, or you have shampoo, liquid soap, conditioner, toothpaste. All of these regular household containers basically didn't used to exist 100 years ago. And what would you do if you needed to have soap? Well, you'd either buy a bar of soap, which is actually, that's going back to kind of interestingly that the world has gone back to using bar soap and bar conditioner and bar shampoo. But in order to have soap in a container that you can basically dispense, plastics became really useful because they could be distributed, they can be stored, they can be dispensed because most plastics are flexible. This is an example of a flexible plastic container for shampoo or conditioner. Have you ever done that where you need to squeeze it a little bit, shake it a little bit? Well, that's only made possible by plastic. Lotion is another good example. So what did you do before? If you needed lotion, you would use actual butter or a bar. And these containers with liquids, all of these that can hold liquids and foods. So what it became is what we have now, this very modern society. It's fast. We can go places quickly. You can grab a bottle of water. You can grab a to-go container of food, of lunch, of dinner, of breakfast. But there's a downside to all that, right? So let's take a look at, we know that polymers are not new. So there have been natural polymers around since the beginning of time. Natural polymers include cellulose in grass, wood, and paper. So cellulose, we learned in module 11, is the monomer glucose, bonded over and over and over again with the linkages that are beta linkages. So that leads to a linear shape of this polymer made out of glucoses. And so we cannot digest those beta linkages. And so we can't eat grass or wood or paper and get any energy out of it, even though the monomers, the glucoses, are very energetic. Okay, this is in contrast to starch in foods. So we also learned in module 11 that when you link those glucoses with alpha linkages, that's the bent V shape, well, that leads to an overall coiled structure of the polymer, which is great for storing energy. And that's what plants do. So plants store energy. They also, they make those glucoses from the sun. Plants are pretty amazing. I know I talked about this in lecture. And plants don't seem to mind if we eat them also. They can overproduce and make enough starch and sugars for humans. And so a plant-based diet is what we did talk about also in module 11. So those are natural polymers of glucoses, the cellulose and the starch. So another example is tree saps that produce latex rubber. Like here's a rubber balloon I have. And rubber is important for gloves, PPE. Well, what originally, this was one of the early polymers that was natural polymer, was discovered, this rubber tree in the middle of the Amazon by European explorers, and that you could take the sap and turn it into a rubber that was a flexible material that just didn't exist in Europe. And so that flexible material became rubber that is now a version of rubber that is a lot better than the rubber tree sap that was produced. Same is true about cotton. So those cotton balls there, cotton is a natural polymer. But what science did is they basically processed these natural polymers like rubber and cotton using heat and pressure, and made a better version of cotton, made a better version of that rubber. And that was the beginning of synthetic polymers, basically trying to process the rubber and cotton to make it slightly better, because this is very close to the cotton that grows naturally, and very close to the rubber that is produced naturally, but a little bit better than natural cotton and natural rubber are these semi-synthetic versions of rubber and cotton. So vulcanized rubber was a lot stronger than the natural rubber tree, and it could handle these swings in temperature that that basically they needed in Europe if you wanted a flexible material that could handle cold or hot. And cotton, and also celluloid, also is a semi-synthetic. This is celluloid that was the origin of filming. So filming natural films in Hollywood, not natural films, but filming in Hollywood, Hollywood films was originally all on this celluloid. So photography, and this is basically capturing an image using the energy, the light energy, and it basically is seared onto the celluloid. And so that is now moving forward all digital, but this is the origin of the whole Hollywood industry, is the ability to capture images on film. Okay, so we're in an age of polymers, and everywhere you look around the house, right in front of you, there's going to be some polymers. Now, the most common are going to be these household containers like polyethylene. Polyethylene is PE for short, and we know that there are two versions of polyethylene. There's high density polyethylene that is more rigid household containers, but still flexible, like this shampoo bottle I showed you. And then there's also low density polyethylene that's a lot more flexible, plastic, like these Ziploc plastic bags or bubble wrap. And so that's everywhere in the house, those two versions of polyethylene. There's also vinyl chloride. This is the strongest of the big six plastics. And the most common that you'll see is credit cards. So the polypropylene is normally food containers, but also is a very, very versatile plastic. And it is, this is a fabric. So one important thing to note is that we have fabrics that are polymers. We also have coatings, the Teflon coatings on a nonstick pan. That's a coating, not a solid. And then there's this very flexible version, saran wrap. And then polystyrene, we know, has two versions, which we'll look at. But the idea of polymers originally was to copy these materials that nature could make. The fabric example, here's a dry fit shirt. So the idea of fabric was the one of the early polymers was silk, or to copy silk. So silk was also complicated, that you had to go get this caterpillar, wait for it to have its cocoon, then take the cocoon and unravel it and use that silk to use the threads of the unraveled cocoon to then weave a fabric that was silk. Silk was very desirable because it was lightweight and flexible. So scientists said, well, can we just make that? And so I showed you that in lab, that nylon was the first, one of the early polymers that tried to copy nature, and nylon thread becomes those silk, is very silk-like. It's strong, it's durable, and yet you don't have to go through the process of getting the caterpillar in the cocoon and unraveling it. You just make it by mixing two organic liquids. So you end up making a nylon thread, and then you can weave that into a fabric. So what the polymers have in common is that it's a monomer bonded over and over and over again, definitely for the 5 we talked about in lecture with the addition polymerization reaction. So that's very simple. It's a starting material that is the same compound. You just have to have a whole bunch of it, and then you get them to bond over and over and over again. Very simple that way. They're generally going to be solids, but not always. Sometimes you have a coating like the Teflon coating, but they are usually insoluble. They do not dissolve in water. Okay, and that's important because most of these containers that I looked at on the first slide, those household containers or these containers, they're all water-based. And so it became a way for industry to sell you stuff like water or those foods that previously 100 years ago, people just had to make all this stuff in their own homes. Thermoplastic means that they can be melted and reshaped into something new. Now that is why plastics are all recyclable. But the idea of recycling is that the plastics need to be separated, and you can't melt down plastic number 4 with plastic number 5. You have to have one separate from 5 before you can melt it down and reshape it into something. And one issue about plastics, a major issue, is that they are not easily biodegradable. They do not decompose easily. So most of the plastics that we have are, that were invented in the early part of the century, last century, they're still around. They just don't break down. They're very, very durable. And that's good in a way if you want to have, you know, a garden hose or a shirt that doesn't break down, but it's bad in that, well, they're around in nature. And one thing we talked about is plastic pollution in the ocean. So plastics tend to float. These are single-use plastics. And that's an issue, is that, okay, the world in the last 15 years, the use of single-use plastics went up exponentially in the last 15 years. And the world cannot handle it. So not the recycling facilities, not the oceans, not even the landfills can handle the amount of plastic that increased. And if you even think about how much plastic use increased just during the pandemic because of people getting takeout, or basically everything that we needed, those, I don't know, all the PPE that came in containers that were also, many of the PPE were also polymers. So these are single-use plastics that the world hasn't exactly figured out the best way to deal with it when it's done with its use. Okay, so the big 6. So you are going to look for plastics in your own homes, and you can look for this recycling symbol, but basically anything that is plastic, whether it has the recycling symbol on it or not, all of those have the recycling symbol. The recycling symbol is basically the company doing that without being regulated, not being forced to. It's basically a good practice for companies. It's just for them to show, hey, we care about the environment. But that doesn't necessarily mean that those containers are going to be recycled. It depends on a couple things. It depends on the consumer putting in a recycling bin. It also depends, more importantly, on the collection of the recycled material actually being recycled. So we'll get to that. But there are over 60,000 synthetic polymers now that scientists really went crazy with it. They said, okay, what can we change up in those polymers and make different polymers that have different properties? And so these are the main 6 that we encounter in every day are these 6. And so you will look for these in looking for some samples around your house. So they might not have the recycling symbol with the number, but most usually do. So the numbers 1 and 2 are the most common. Number 1 is soda and water bottles. Those are generally going to be clear and lightweight. And that's one thing, they're lightweight and inexpensive containers. And so those lightweight and inexpensive containers are what companies want. If they want to sell you water that already is free, they don't want to pay very much for the container, and they also don't want to pay very much for shipping the container. So they want it to be as light as possible. So this water bottle, this type of water bottle here, these are clear, and this does not have a recycling symbol on it, but it is plastic number 1. This is the most common. The next most common is this plastic number 2. So these tend to be stronger bottles, and these are household containers that are still flexible. This is an example of a bottle that is translucent. Light will go through this, but you can't see through it, which means it is also opaque when you can't see through it. Okay, this is another example of a bottle that is translucent. So light will go through it, but I can't see through it. Okay. This is another example of something that's opaque. So this is a lotion container. Definitely can't see through this, and light doesn't go through this. So that's the meaning of opaque. You can't see through it. So those household containers, they are everywhere in the house, and plastic numbers 1 and 2 are the most common plastics. Then you've got polyvinyl chloride. That's plastic number 3. And there's 2 forms of this. There's a rigid form that is the strongest plastic. This is an example of plastic number 3. This is the strongest plastic, and it's generally used to replace metal. So it's used in pipes to replace metal pipes. But what you will have is your credit card is almost always plastic number 3 PVC. And you can look at that credit card. It won't have a number 3 on it, but it is plastic number 3 and in theory recyclable. But one thing I've talked about is how anything that's smaller than the palm of your hand cannot be recycled, because it basically gets caught up in the recycling facility and falls through the cracks. And so those tend to get thrown away. So it's best if you just throw them away. An example of that is the lid on a water bottle. The lid on a water bottle, this is usually plastic number 2 and it's recyclable, but only if you put this lid back on so that it doesn't get lost. In fact, I want to show you this, is that on this, this bottle, the label actually has the instructions saying, in order to recycle this, it says, empty the water and replace the cap. And so I would empty this water and replace the cap. And I also take this label off when I put that in recycling. Okay. Number 4 is low density polyethylene, LDPE. So those are those grocery bags or bubble wrap like this. This is came in the mail yesterday, this bubble wrap from Amazon Prime. Well, notice that this is a very special plastic that, even though you can melt it down, this requires store drop off. And I'll show you this on the label. Actually, let me switch to here. Is that on this label? Can't find it. Hold on. Looking for my camera. Looking for my camera. Okay, so on the labels, they are often now giving instructions on exactly what to do to recycle these things. And so let me switch to that. Can't find it. Oh, here it is. Okay, so on this label, it is telling you to remove the paper label before recycling. So there's a shipping label. So I would take this off. And then it also says it requires store drop off. And so that's store drop off. And this is a site that I mentioned in lecture. It is called howtorecycle.info. Anytime you're wondering, gee, what do I do with this or that or the other thing? This is an example of bubble wrap. So this bubble wrap doesn't have any recycling number on it. Neither will any Ziploc bag, but that is recyclable. And so this is recyclable, but only when you collect it all and then bring it to a store. So that's plastic number 4, requires special collection. Okay, so and that's what I do, is I basically have a big bag of bags and take those in a couple times a year. So polypropylene is plastic number 5. And this is generally food containers because this is resistant to oil. So any of your containers that are takeout containers are generally going to be plastic number 5 and not always marked. And so those are recyclable. And one that is most commonly not known to be recyclable, or that people realize, is polystyrene. So there's 2 forms of polystyrene. One is styrofoam, and the other is the crystal form. So let me show you both of these. Polystyrene is recyclable, and showing you both of these here is that this is polystyrene is your styrofoam cup. So that is Oreos out of here. The styrofoam cup So this is the same thing as this polystyrene, which is a very clear, almost replacement for glass. And this is crackable. Notice that I can do that to it. Same thing with this styrofoam. I can actually crack that too. It's the same material. And the difference between this cup and this cup is that this styrofoam cup, how do I get that sun out of here? Okay. This styrofoam cup has a lot of air blown into it, and that makes it a very good insulator. So this is a glass-like replacement. And you'll notice that there is a plastic, there's a number 6 on the bottom of that. And so that's what you're looking for, is try to guess what the plastic is. Can you see that 6? Try to guess what the plastic is based on its properties, and then see how good you are at that. Okay. What I have an example here is just a paper cup. And so if you're given the choice of paper, styrofoam, or plastic, the best option as far as being biodegradable is this paper cup. Okay. And those are all considered basically single-use plastics. Another example is this boxed water versus this metal versus this. Well, the best option is this biodegradable. And in fact, this lid even tends to be a plant-based plastic. And so being biodegradable and plant-based, can't go wrong with that. This metal is generally, metal tends to be recycled much more than plastic. And that's because metal we have those facilities set up in the US because 50 years ago, there were a lot of metals in aluminum cans, soda cans, and soup cans, or all kinds of cans for food. And so the US has the facilities for recycling metal and does tend to recycle metal. Okay, so let me go back to here. So in looking around at the different types of plastics in your home, be on the lookout for all of these plastics, because in the next part A, this is part A on your lab report, you got to go find 3 different plastics. Look for those 1 through 6 numbers, or from the descriptions I've just gone over. And you want to find 3 different plastics, okay? And they don't have to be plastics. Remember, you can use a fabric, or you can find this bubble wrap. And what you're going to be doing is analyzing these physical characteristics, which is by looking at it, you can find out if it's clear or opaque. And remember, opaque means you can't see through it. Okay, so sometimes you think, so why does it, opaque is either yes or no. So why does it say both? Both is if you have 2 samples that both plastic number 2, let's say, and one you can see through and the other you can't see through. That's why you would write both. But generally it's going to be yes or no for clear or not. Like is this clear or not? Yes or no. Is this clear or not? Yes or no. Okay. Flexibility. So flexibility, can you bend it? So being able to bend something. So here's an example. Can I bend this metal bottle? Nope. Can I bend this? A little bit. So, and then durability. So durability speaks to its hardness. Is it hard like that? Or is it kind of a little not as hard, kind of softish? Breakability is, can you crack it? Can you basically squish it in your hand and it'll crack? Like that, I could squish it, but it didn't crack. How about this one? I could squish it in my hand and it didn't crack. Okay. And then recyclability, yes or no. Okay. So this is going to look at part A on the lab report. Let me switch over to that. Is going to here. Okay. So you have part A on your lab report where you're filling out these physical characteristics of 3 different samples. Okay, and you want to include a photo of those 3 samples that you used and make sure that photo shows those recycling symbols so that I know what your plastic numbers were. Okay, and so you can go by the lab procedure and look at the different types of plastics, but you have plastics 1 through 6 that you want to look for. Recyclable. Plastics are recyclable because they are thermoplastic. They can be melted down and then remade into the same exact plastic. So this is why the industries developed this symbol, which is the recycling symbol. It's 3 arrows, and those 3 arrows stand for the 3 words: reduce, reuse, and recycle, in that order. And so reduce is number 1, which is reduce the amount of plastic you use in the first place, whether you just don't buy the plastic. That would be great. That would be number 1. And sometimes that means, not getting the plastic water bottle and, the using your own water bottle. Or for me, what that means is going to the farmer's market to buy apples, because the only way you get apples at Trader Joe's is in a container. Or even plastics, using less plastic. So when if given the choice, something that is partially plastic, let's see if I have an example here. Here's this Oreo container. This Oreo container, for instance, there's some plastic involved. And so if I'm choosing between Oreos that I like or cookies that come in a container that does not have any plastic, I get the other cookies. This I had to, I had a recipe. But this idea of reusing plastics, this is a great idea too. That doesn't always happen though. So the idea is if you have your own plastic bags, and then you don't ever need to use a plastic bag. This is the problem that I find, is that those bags that you have instead of plastic bags, now I've got too many of those. So those kind of semi-fabric, those are actually a polymer in themselves. Also too many of those. Recycling though is 3rd. So that's last on that list. And the idea is to put things in the blue bin, but in the proper manner, understanding how the recycling works. And so we'll get to that in the next slide. But number 4, the last is, these are new, is refusing the plastic in the first place. Someone's trying to give you a fork, or someone's trying to give you a free bottle of water. Give it back. I'm constantly giving stuff back, saying no. And even though sometimes the thought is, well, the plastic already exists, well, the more of it that they have on hand is the less they have to buy, or the more of it that gets given back, the more that these companies will start to understand that people don't want this plastic. In fact, it's just a new bill that was passed that the city of Los Angeles is requiring restaurants to ask if you want a plastic fork or a napkin, instead of actually automatically give you plastic forks and napkins with to-go or takeout. And then recover. So remember, plastics come from oil. Mostly are coming from oil, not all plastics. We looked at in lecture a corn-based plastic that is biodegradable and compostable. But because plastics come from oil, they'll burn, just like oil will burn and can be used for energy. So we can, in theory, use this for energy. Okay. But the reason why recycling is kind of problematic is because most cities are set up in what's called single stream recycling. And so that basically says throw everything into the blue bin: paper, plastic, metal, and it causes a problem at the center where it's all collected when all this stuff is mixed up together. So let's switch over to this video screen. Let me find it. No, not that one. Okay, switching over to this one. So I think we got a chance to watch this in lecture, but always good to be reminded of what is going on with those plastic bags, that very flexible plastic number 4.
To recycle plastic bags at home. But why? The bags are made of recyclable materials, but recycling companies don't want them in your blue bin. Seems strange, right? It's due in part to single-stream recycling, which is common in many communities. It works like this. You toss everything into one bin, and it all gets sorted at the recycling center. Special gears separate flat items, like paper and cardboard, from bottles and other containers. Air jets split lightweight bottles and cans away from glass. Electrically charged aluminum cans are repelled into their own stream, while magnets pull out tin cans and other metals. And after a beam of infrared light detects up to 7 types of plastic, a blast of air sends them along individual paths. The end result is huge bales of sorted materials, which are sold to paper mills, metal foundries, and plastic makers. So, what's the problem with plastic bags? The first complication occurs at step 1, the single-stream recycling bin. Here, bags get wet and dirty and become too contaminated to sell. Second, there's no mechanical process for separating plastic bags at recycling facilities. And a recycling industry representative said there's not enough staff or money to clean and dry the dirty bags. Instead, they either get tangled up in sorting equipment or accidentally end up in bales of separated paper. And if just 0.5% of a bale is contaminated by other materials, it can't be sold to reuse companies. In the end, most plastic bags are removed by hand and dropped in the trash, even if recyclables are inside. So, what can you do? Clean and dry plastic bags are still recyclable, but they must be dropped off at specially designated collection spots, like the ones you see at grocery stores. From there, companies buy the bags and recycle them into hard, durable plastics, like patio furniture. If you must choose between a home recycling bin or the trash, the recycling industry suggests throwing plastic bags in the trash. It might feel wrong, but recycling centers say it helps more materials get recycled. Another option, don't use plastic bags. Opt for paper or cloth bags instead.
That's the idea, is that understanding exactly what is recyclable will help the single stream recycling process. Let me show you, go to here. Nope, not that one. Hold on, finding my other screen. Okay, so I'm trying to understand how to deal with something like this. When you have a container that is mixed up, has all different types of materials, this Oreo container is an example. Well, first of all, you can't have any food in there. So take those 2 Oreos and eat them, and set them aside and eat them later. And inside you have plastic. So this plastic is usually, this is plastic number 6. I can see number 6 symbol on there. This can go in the recycling bin. This outside is this silverish stuff called mylar. So we talked about mylar, and mylar is layers of plastic and metal. It's a flexible, it looks like metal, but it's flexible. Anytime you see something that is flexible and metal, that's mylar, and mylar is not recyclable. And so mylar is an example of something that does not go in the blue bin, but in order to really fully deal with everything, you have to deconstruct lots of things before they go into the blue bin. So let's take a look at this. Going back to here is, so you know that about plastic bags, is plastic bags. This includes this, this Amazon, this bubble wrap. These cannot go in the regular blue bin because it's single stream recycling and it gets stuck. And so that means don't recycle them at home, take them to a store drop off. Okay, and so what goes into the blue bin? What actually goes in there are the recyclables that are all those plastics, plastic 1, 2, 3, but not 4. Number 5 and number 6 can go into the blue bin. So those are those plastics, but not number 4. That's the low density polyethylene, that very flexible plastic. Okay, so almost all the plastics can go in there. Will they be recycled? Hopefully. Right now there's a trade war between the US and China stopped taking all plastics from Europe and the US. Not that it was their responsibility to take it, but that all the plastic in the world is basically not really being recycled right now, that the facilities are not set up in Europe and the US to deal with their amount of plastics. So Europe and the US have got to ramp up their ability to recycle plastic because China's not taking it anymore. Paper and cardboard. So how to deal with paper and cardboard like this box. So it needs to be empty and it needs to be mostly clean. Most importantly, having no grease. Okay, so no grease or oil, because the way paper and cardboard is recycled is different from plastic. They don't melt down paper and cardboard. What happens to paper and cardboard is it's separated out through blasts of air, so it also can't be wet. It has to be dry, dry paper, dry cardboard. So those are cardboard boxes like a cereal box or this box water. This should be ideally dry and empty, and it will separate out at the facility. And what happens is they take all the paper and cardboard and they shred it and then they pulp it, adding water to it. And when you have grease or oil, like a greasy pizza box, that oil will float to the top of the pulped paper, and then they can't use that pulped paper mixture. So that's why you can't have it wet, so it will separate out if it's dry, and you can't have it greasy because then it'll make the whole vat unrecyclable. So metal, like a soup container or a soda can, this also needs to be empty, but it doesn't have to be perfectly clean, just has to be mostly clean. And the same is true about glass. Metal and glass. So let's say you have some pasta sauce in a glass jar. That has to be empty to get rid of the pasta sauce, but you don't have to wash it out. It just has to be mostly clean. The reason is because for plastic and metal and glass, what is done in the recycling is it's heated up to a very high temperature, and the food bits, the residual food, will melt off and burn off before you get to the melting of the plastic or the metal or the glass. So that's why it just has to be mostly clean. So you can just say, for instance, eat yogurt, wipe it out, eat all the yogurt out, and you don't actually even have to really, you don't have to wash it out. Okay. We know that there's separate collection for plastic number 4. That's that very flexible plastic, low density polyethylene. And so look for that, and that's your separate collection and store drop-off. Hazardous waste. So hazardous waste are your household chemicals. The most common chemicals that you have in your house is paint. Okay, so let's say you took an art class and you have some paint. That's considered hazardous waste, and that is hazardous waste collection. So there's collection sites for hazardous waste. Santa Monica has one. UCLA is open for hazardous waste on certain days of the month. And the most common you'll have is paint. Dead batteries. So dead batteries are considered hazardous waste. But the interesting thing about dead batteries, okay, so first of all, why is it hazardous? It is because batteries have metals in them. So there are metals like lithium and copper and zinc, and those metals can be recycled if done properly and taken to battery recycling. Okay, so you can recover those metals, and those metals are worth money and can be made into new batteries or other metal products. And so they are, however, also in the batteries is acid. And acids and sometimes bases also are in batteries. Those have to be dealt with properly. And so that's considered hazardous waste. So batteries can have either separate battery collection, that's also store drop off. I've seen battery collection, or hazardous waste also is a good, is for batteries. Mylar. So Mylar has to go in the trash. So that's the black bin. Or it has to be sent to a company that deals with Mylar. An example, so Mylar are bags of chips are most commonly, or as I showed you, this Oreo container. Mylar, what it does, the advantage of it is these are foods that need to be kept fresh and airtight. And so it provides an airtight seal and yet is flexible and lightweight. And so this is, you know, I just, Looking at that, can't believe we ate all those Oreos, and also can't believe I bought this container. So the Mylar though has got to be, cannot be recycled, cannot recycle the metal, cannot recycle the plastic, and you can send it to a company called TerraCycle. Now I can tell you that I've been saying that for years and don't actually send any of that Mylar in. I mostly just try to refuse or not buy it in the first place, or that it has to go in the black bin, the garbage. And then there's e-waste. So e-waste, zooming in on this, is anything you plug in. So those are your electronics. It can be a TV, a computer, even things that you plug in and charge temporarily, like an iPhone. Well, all of those things that are electronics have metals in them. Even rare metals like cobalt and indium and gold. We saw that way back in the first week discussion of Chem 9. Well, those metals can be recovered, but they have to be sent to a proper facility. So e-waste collection is really important to understand that you'll be doing the planet a favor when you take your electronics and properly recycle them. And so that's even something simple like a hair dryer. Anything you plug in is an electronic, and that can be needs to be dealt with as e-waste. Okay, so even little things like if I have a little flashlight, it's a battery. I'm like, this is kind of electronic. I put it into e-waste so that hopefully those materials can be recovered. Okay, and so companies have tried with the labeling to explain exactly what to do. So this 3-arrow recycling symbol means that, yes, you can recycle this, though it does depend on your certain community. So sometimes it'll say check, because some plastics, some communities don't take plastic number 4 or plastic number 6 even, okay? Then there's stuff that can't be recycled at all, and that is usually the case for Mylar. In fact, I'm gonna look at this. So on this Oreo bag, this has the can't be recycled, and that explains that it is the multi-layer wrap, which that's the Mylar, okay? But it does say that to check the plastic tray, if that is accepted, it's plastic number 6. And so that store drop-off is usually plastic number 4, okay? And so make sure you know that you can collect plastic number 4 indefinitely. It doesn't go bad, and then take it in when you're done with it, when you've collected enough. So howtorecycle.info is something to look up whenever you're kind of wondering exactly what to do. And that will help you, guide you in properly disposing of things. Now, understanding the chemistry of these synthetic polymers, these plastics, the reason why they're recyclable in the first place is because they all start the same monomers. And so when you have this monomer called ethylene, so this is the simplest monomer, it is 2 carbons. And you'll notice that prefix eth. That E is the E in the mnemonic mother eats peanut butter. Those are the first 4 carbons in the hydrocarbon family called alkanes. And so 1, 2, 3, 4 carbons. And so this means 2 carbons, and ethylene is specifically the monomer that has 2 carbons with a double bond between them. So notice that double bond. And what happens in the addition polymerization process is that you have a reactive catalyst. And the reason why that is a reactive catalyst is because there's a lone pair electron. So a single electron, an unpaired electron, not a lone pair, but a single electron. And we've seen that before. That was the reactive catalyst of chlorine that breaks down the ozone layer, ozone in the ozone layer. So using a reactive catalyst here in this addition polymerization, what it does is it causes this double bond to break and become a single bond. And when there's a single bond between those carbons, that allows for bonds to form on either side of the monomer. And so now the monomer can link up to other monomers on either side. And so however many monomers you put into it, this is a coefficient, becomes a subscript. And so this is in general, once you add the catalyst in, it causes all the monomers to link up. And so you can have 2 or you can have 1,000, but as many monomers that go into the original reaction will then all be bonded together. So this is to note that this is a double bond. In this first monomer becomes a single bond. And then attaching it, there's a new bond. So this is a new bond on either side. And so this is the second monomer, also becomes a double bond, and then it can bond to, in green, a new bond. Okay, everything else stays the same though. Those 4 hydrogens are still the same, 1, 2, 3, 4. And they're still the same 1, 2, 3, 4 as the monomer, and they're still there for the polymer. So what scientists said is, can you change the monomer and get different polymers with different properties? And so the addition polymerization of polyethylene was just the starting point. And by varying the monomers, you could create all these different polymers. So vinyl chloride is an example where just changing one of those hydrogens to chlorine creates this very strong plastic, polyvinyl chloride. Remember, that's the one that can replace metal. Or changing one of those hydrogens to a carbon group, CH3. So now it has 3 carbons, and this is called propylene, because in that same alkane family, mother eats peanut butter, P for propylene, that means that there's 3 carbons in there. Okay, and then there's, so this forms polypropylene, which is the plastic that's resistant to oil and used in food containers. And then you got styrene. So styrene, this C6H5 is a benzene ring. It looks like this. Okay, and it is a ring with 6 carbons and 3 double bonds. And this changing that one hydrogen and then forming the polymer gave polystyrene, which has those 2 versions, the styrofoam. That is called the expanded version. It's expanded because there's air blown into it. And then there's the crystalline version. That's the one that looks like glass. Okay. And so all of these monomers, once you have the changing one of those hydrogens, they are no longer symmetrical. So they're asymmetrical, which means they're not the same on both sides. So you can assign one side different from the other side by calling one side the head and the other side the tail. Okay. So, and you get to assign that. So you get to decide, okay, I'm going to call this side with the chlorine the head, and then the other side by default is the tail. So then when building the polymer, this allows for different arrangements where you can have a head to tail arrangement. So here's the head of each monomer, and then attached to the tail of the next monomer, or the head here. Then this forces the tail to attach to the tail of the next monomer. So that's tail to tail, head to head, or a random arrangement where there's no pattern. Okay, so that is only possible for those monomers that have the asymmetric, that they are not exactly the same on both sides, because ethylene is exactly the same on both sides. So that cannot have a certain arrangement. Okay, so let's take a look at these density tests. Okay, so one way that recycling facilities deal with single stream recycling is by separating out everything first by using, I think it was light lasers, and then also puffs of air. And then the plastics can be separated out also with air, but also by using density of these samples in water. So you can put these plastics in water and some will float and some will sink depending on the density of the plastic. Okay, so when you drop a sample into water, that sample will either sink or float depending on the plastic itself, its own density. So here you have these approximate density values of these plastics. And then depending on the liquid you dump it in. Okay, so let me show you. This video is an example of a density test. So let's go to here. Not this. Okay, this one. So here's an example of a density test. Here's a close-up of a test tube. And in this test tube, there's water. And then I'm going to drop a sample into this. Okay, so there's water in the bottom of this test tube. So this is a sample of plastic number 1, PETE. And that plastic number 1 has an approximate density of 1.38. Okay, so this is water, and the water has a density of 1.00. So 1.38 is greater than 1.00. So what happens when the sample of the plastic, let me pause that, when the plastic, which is 1.38, has a greater or a bigger density value than the water, which is 1.00, that means that this plastic sample will sink. Okay, so that plastic sample fell to the bottom of that test tube. There you go. So that is an example of plastic number 1 falls to the bottom of the test tube containing water. Now here's a sample of plastic number 2. So plastic number 2 is 0.95. And so there's the sample. It's going to be dropped into the water. And let's see what happens when you drop this one into the water. It floats a little bit before falling down. You sure about that? Let's try that again. Let's drop that in. Plastic number 2. Okay, there we go. It floats. See, so that floats. And that's what we would expect. So plastic number 2 has a density of 0.95. That's less than the density of the water, which is 1.00. When the plastic density is less than the density of the liquid, the water, it will float. So that's what's going on, is that you can take all your plastics at a single stream recycling facility, dump them in water, see what floats and what doesn't, and then you will separate out the plastics by their densities. So let's go back to here and show you this chart again. So this is in the lab procedure, this table that you will need for part B. Okay, so this is the density values of those plastics. So for instance, polypropylene has an approximate density of 0.90. And so if it is dropped into water, and water has a density value of, the density value is 1.00, this 0.9 is less than 1.0. So if the density of the plastic is less than the liquid, it's going to float. Okay. Or you have an example of polyethylene. This is PET. The bottom one is 1.38. And so if you drop that sample of PET into water, it is 1.38 is greater than the water. And so if the density of the plastic is more than the water or the liquid, the plastic's going to sink. Okay, so water is just one test. So let's go to the lab report and show you that the part B, oops, let's move this here. In part B, these are density tests, and you can use different types of solutions to test the different densities. And so what you want to do is transfer those approximate density values to this column, this first column here. And then these are liquids that are used to test. And the test is float or sink. And so basically, I think the polypropylene was 0.9. So let's write that in. So that was 0.9. And so when you compare this to the density of this liquid methanol is 0.79. So this is less than, or this plastic sample is greater than. So what happens when it's greater than is that it will sink. Okay. Or if you drop that sample into this mixture, 1.1 ethanol and water, that has a density of 0.94. Well, this 0.90 is less than 0.94. So that means this plastic will float, okay, in that liquid. So depending on the density of the liquid, your plastic's either going to float or sink. So you have to compare to the density each time. So start with the given density from the lab procedure. So have those from the lab procedure first transfer them over into this column, and then you do an analysis. And then you'll be able to rank the relative plastic densities by putting the lowest and use the acronyms in here. Use the acronyms or the numbers. Like plastic number 1 would be the lowest, or plastic number 6, the lowest, depending on the lowest values versus the highest values of those densities. Okay, so that's how you're going to fill in part B, the density tests. Okay, so you guys know where to look for this. So let me give you some time to fill this in. So complete part B using the lab procedure. And those are the density tests. Okay, so I'm going to give you about 15 minutes, including a 10-minute break. So this is 15 minutes, including a break. And so we'll be back at, let's say 11, a little bit after 11:30, 11:35. So this is the story of electronics. Back when I was talking about the different special types of recycling, so store drop-off, well, electronics or e-waste is one of them. So this is part of the Story of Stuff series. It's an 8-minute video, and there are embedded questions. So I'm going to give you about 10 minutes, maybe a little bit more than 10 minutes, about 15 minutes to complete this assignment. This is you'll find this in a few places. It's linked in today's lab, but it's also in your upcoming assignments that are due. So let's give you 15 minutes to complete this assignment. Okay, so if you are already there and you are thinking about breaking free of your plastic habit, so part of it, remember, is we have no choice. Sometimes you want the Oreos, but it's only comes in a Mylar container with a plastic part of it. So you have to change your lifestyle. Sometimes that is just a fact of life, or buy bar soap instead of liquid soap, or shampoo bar versus the shampoo that comes in the container, bottled water versus boxed water. You have to make those choices. And the thing about some of these choices right now is that they're more expensive. So that metal bottle of water, that costs 3 times more. And let's already talk about the fact that we know from the story of the plastic water bottle that it's 2,000 times more than water that is basically free. So let's not fall prey to stuff being pushed on us, and not basically be a victim of marketing and these campaigns where they're trying to sell us stuff that you don't really want. So the idea is just think about your life and what can you cut out of your life. Some of the easy things are the shopping bag, those water bottles, cutlery I already mentioned. There's legislation. And the next time as a voter, you see a bill or a proposal in your city to get rid of plastic, or even at Santa Monica College, it was a student group that brought the basically lack of straws. So no more straws available at the Santa Monica College campus. And that was pre-pandemic. And so it has spread, though, the idea of, hey, do you really need a straw? Can we get away with no straw? And so not always, but many times, or the paper straw. And it takes a little bit of getting used to. Paper is not as great. It decomposes sometimes. But really, when you're thinking about the single-use plastic straw, sometimes it's worth it. So skipping plastic produce sometimes means not buying the thing that's wrapped up in plastic, or a bag of apples, and going for the apples that are individual and not even putting them in a bag at all. I just put them right on the conveyor belt, or right into my bag that I'm buying. So the idea of refusing plastic is the best thing all of us can do. Another thing that all of us can do is, we talked about this in the plastic pollution discussion, is beach cleanup is great. Even better than that, just pick up plastic, just outside your own house. Pick up anything just outside your own house, because all that stuff ends up getting washed into the ocean. And it's not that people are dumping off plastic bags into the ocean and they end up on this, stuck on this turtle, is that these plastic bags are very lightweight. They float in the air and they float in water, and they just end up in the ocean and they stay there. And so if anytime you pick up stuff that's outside, and I tell you that this is something that I try to do when I'm on my way back, or just walking around and I see plastic or I see garbage, I will pick it up. I'm trying to basically take control over some of this situation that is just garbage everywhere. So this is getting us to part C, which is making a polymer in your own home. And so this is completely optional. And I've made a video of it, and I made this polymer, which these ingredients you might already have if you've made any slime recently. So having liquid glue, so that's the Elmer's white glue, water. Borax is the one that you don't normally have. Borax is a special cleaning solution used in homes. You can get it at the hardware store, but borax is needed, and we have it in the chemistry lab, which is why I was able to make these. But when you make slime, it's glue, water, and borax, or you can use liquid laundry detergent. But those three components make that slime that is viscous, a viscous kind of liquid that flows. Well, once you add cornstarch, you can make a ball that bounces. And so this is a polymer ball, and I'm going to put this link in the chat to collect the data, but this is going to be data for part C. So I'll show you all this on the lab report. Let me switch over.